Okay, yes, so this is my third and final lecture. So yesterday we looked in detail at the p-adic determinant method, and the plan today is to look at other versions of the determinant method, and in particular we'll look at the approximate determinant method. So one of the things that we saw last time was that we will produce auxiliary forms fj that the points we're interested in must be zeros of. And for this to be useful, it's important that f and fj should be co-prime. If fj turned out to be equal to f, we would get no extra information, for example. And we did that in a rather cack-handed way by only using monomials that had no terms in xn to the d or larger, that the exponent of xn was an en strictly less than little d. So in general, in the determinant method, your choice of monomials is an important decision that has to be made. Now, there's an alternative viewpoint on this, which is a little bit more sophisticated and therefore a little bit more complicated, but may be interesting. So let's have a look at that. We'll let the hypersurface f equals 0, we'll denote that by v. And this time we're going to consider all the degree d monomials, x to the e. There will be this binomial coefficient k monomials in total. And we'll list these as m1 of x up to mk of x. And then we have this kth power map that goes from z to zk. It takes x to the string of all the possible monomials. Now, if we have a point where f is equal to 0, then it's also true that x to the f times f is equal to 0 whenever we have a monomial x to the f. And if we make it of degree capital D minus little d, what we will have here, x to the f times fx, that will have degree capital D. So there are a large number of forms of degree capital D constructed this way that have little x as a 0. So for a particular exponent vector f, let's denote x to the f times capital F by this sum of monomials with coefficient ck. So in fact, the coefficients ck are basically the coefficients of capital F, except now things are bulked up to make degree capital D rather than little d. So the rational points on our variety are now mapped to not just into zk, but they're mapped into the points where x to the f times capital F vanishes. That's to say the points where ck mk of x vanishes, and so we end up in this linear subspace of zk. And of course, this is true for every exponent vector f. There are many choices of exponent vector. So in fact, we end up not just in this linear subspace, but in a sublattice defined by the intersection of all these HFs for the various possibilities for f. And it turns out that these sublattices are all, that these subspaces here are independent, and so we get a sublattice which I'll call lambda, whose codimension is this quantity, which is the number of possibilities for f. So we've mapped from the set of integer zeros of capital F to this sublattice of zk of codimension of this quantity here. Sorry, I should strictly speaking say v of z here, shouldn't I? The z points on v. Okay. And the dimension of this lattice, well, this is the dimension of zk. This is the codimension I just mentioned. This difference is exactly the number e that occurred in lecture 2. So previously, capital E was the number of monomials in which xn occurred with degree less than little d. And now it's the dimension of this lattice that we're producing. Now, you will recall, I hope, from lecture 2 that we had this quantity st, this set, which is the set of integer points of height at most b, where x is projectively congruent to a given t. And what we showed was that the determinant of m1 from lecture 2 is divisible by a large power of p. And what happens by a somewhat similar argument is that when we map st under this case power map, we end up in a sublattice of lambda defined by various congruences modulo p. For exactly the same reasons that the coordinates of x can be expressed in terms of each other using the implicit function theorem, and that creates lots of divisibilities by p. And it turns out indeed that exactly the same argument shows that the determinant of this sublattice lambda pt is again divisible by this large power p to the v. So we split the points up according to the different values of t, and st then gets mapped to this sublattice lambda pt inside lambda inside z to the k. Now this lattice lambda pt will have various successive minima. I hope you are familiar with this idea of successive minima. The product of these will be at least of order the determinant of lambda pt, and so the largest of them, lambda e, will be at least of order p to the v over e. This number here is divisible by p to the v. It's at least p to the v in size. So we found that the largest successive minimum must be pretty big. And indeed, if it's bigger than capital B, that's larger than the size of any of the points we're interested in. And that's enough to ensure that the points of ST must be on a further sublattice defined by the vectors corresponding to lambda 1 through to lambda e minus 1. There can't be a component in the lambda e direction because that would be too big. So this argument with successive minima actually produces a sublattice of the original one. And what that means is that there's a new relation of the type ck mk equals 0, not of the type that we originally had. So the original lambda was defined by the obvious relations of this type. We've got a linear subspace, so that's given by something new. And that corresponds to a new equation, fj equals 0. Now, I've skipped over a lot of details there, but what happens is that you recover the previous results without having to use this artificial device of restricting the monomials that you use. And it's framed in terms of lattices. Now, there's one important feature here, that we constructed our original lattice by using equations of the type ck mk sums to 0 corresponding to this polynomial equation. And the ck, as I said, were effectively the coefficients of capital F. And that means that lambda, det lambda, depend on capital F, the coefficients of capital F, and the determinant of lambda will get large as the coefficients of F grow, in a way that you can make precise, but it's a little bit complicated. Moreover, one sees, so I've said previously that P to V divides the determinant of lambda pt, but in fact, the same argument shows that it divides the index of lambda pt in lambda. So not only is this determinant divisible by a large power of p to the v, it's also divisible by the determinant of lambda. And so not only do we get an improvement as p to the v grows, we get an improvement that depends on the size of the coefficients of F. And this formulation leads to the following result due to Ehrenberg and Venkatesh in 2005. And one can prove things for higher degree varieties, higher dimensional varieties, but this is what happens for a projective curve. If you have a projective curve given by f equals 0 with a primitive integer form f of degree d, then the projective count of points is not just b to the 2 over d as we saw before, but you get a saving depending on the size of the coefficients. You save norm f to the minus 1 over d squared. So what this means is that, in a sense, the more complicated your form f is, the better the result is. Not only in the sense that the larger the degree is, the smaller the bound is, but also the larger the coefficients are, the smaller the bound is. So that's really rather elegant. And there are other advantages of this formulation in terms of lattices that come about if you try to count points not in a cube of size b, but in a box with different side lengths. Okay, and now I want to mention briefly the global determinant method formulated by Salberger. So previously we talked about the p-adic determinant method, so this is a more global idea. So in this formulation, again, you produce a matrix, which I'll call E1, of degree d monomials. We'll do this trick of restricting the final exponent to be strictly less than little d. But this time, we're going to allow the degree capital D of our monomials to depend on b as well as everything else. And previously, we had one row of the monomial for each point in the set capital S of bold T. We had to split our points up into different congruence classes. But now we're just going to have one row for each point of SB, for each of the points we're trying to count. And we're going to look at the various subdeterminants of A1 and think about how large they are, and in particular, what powers of a prime P will divide the various subdeterminants. So if you've got a particular P, let's try rearranging the rows to put points in the sets ST together. And then just as before, for points lying in a particular congruence class modulo P, all predictably equivalent to t, the A by A determinants, if you have this many points in ST, will produce a large prime power factor p to the VA. So let's see what this looks like pictorially. Here's a very simple example where the number of points, non-singular points modulo p is just 2. So there will be a group of rows here of size A, there'll be B rows here. So there'll be, this will be for the first value of t, this will be the second value of t, and then at the bottom we'll have some rubbish corresponding to singular points. And what I'm saying is that here, all the A by A determinants are divisible by a large power of p. In the next block, all the B by B determinants are divisible by a large power of p. And then here, we can't say much. But overall, if there are capital E columns across here, this is enough to show, very roughly speaking, that something like p to the VA plus VB divides any E by E determinant formed from this matrix. Just because the first block contains lots of p powers, the second block contains lots of p powers. So that means that if this has width E columns, the E by E subdeterminants are divisible by a large power of p. And this is true for any prime. You'd have to rearrange the rows differently, but you get a similar conclusion. So these determinants are divisible by a product of prime powers for suitable VPs. And now we play the same game. We have an estimate for the Archimedean size of these determinants. We compare that with the divisibility constraint. We deduce that the determinant is A2. Determinant A2 is equal to 0, and therefore that the rank of the entire matrix is strictly less than E. And we conclude that there is a form F0, a single form F0 of degree capital D, such that F0 of x is 0 for every point x in SB. So in the old method, the p-adic method, you produce a number of auxiliary forms Fj, which covered the points in SB. Here you get a single form. As you see, it's a global argument. We use lots of primes. You could, in principle, exclude primes if they were particularly awkward, but in general, you just include all primes. But to make this work, you at the very least need the number of columns to be large compared to the number of points modulo p for the primes you're using. And that means that the degree of this form F0, capital D, must grow with respect to B. And in fact, the constraint you get is that you take D to be up to size B to the E, where E is this quantity. So capital D will be a positive power of B. So we construct a single auxiliary form of large degree that covers all the points we're interested in. Now I should stress that just how large you're allowed to take D is absolutely crucial. It's quite easy to construct an extremely large degree polynomial or form that covers all the points in SB, or indeed covers all the points, whether they're in zeros of F or not. A sort of space-filling curve, if you like. But that will have very large degree and large size, so it's important just how big E is going to be here. Beyond knowing the degree of f0, we don't have a lot of information. To compare it with what we did before, let's imagine that f0 factors into linear forms. So the number of linear forms will be the degree, it will be capital D. So we would get b to the e linear forms which covered all the points in SB. And here's the value for E. Now in the p-adic determinant method, we covered all the points with this many forms, Fj. So if you compare the exponent here with the exponent from the global method, you see that they differ by this denominator factor d to the, n minus 2. So Salberger's global method can be thought of but as improving things by this factor n minus 2 in the denominator. So that makes no difference when n is equal to 3, but it's already better for n equals 4 and higher. However, the difficulty with the global determinant method is that f0 could alternatively be an irreducible form of degree capital D, and then using the previous information is difficult for forms of unbounded degree. All the estimates we had previously, like this one here, involved an implicit constant depending on degree, and if the degree is capital D, we don't know how things depend on capital D. Nonetheless, this awkwardness was handled by Salberger in the case n equals 4, so this would be projective surfaces, using what he calls the semi-global determinant method. So I think this is an interesting area for further research to try and make more use of the global determinant method. Okay, so I'm going to devote the rest of my time to talking about the approximate determinant method. And I should stress that this is a method rather than a theorem. So there is no one result that sums up what the approximate determinant method does. You have to adapt the procedure depending on the problem you're trying to attack. And so I'm going to illustrate it by examining the counting function for integers up to x, for which n squared plus 1 is square free. And there's a theorem of Esterman going back to 1931 that says that the number of n up to x, which n squared plus 1 is square free, has an asymptotic formula with leading terms c0 times x and an error term with a power saving. The leading constant is this thing here. It's an infinite product, convergent, positive value. And in Esterman's theorem, the error term is x to the 2/3 times log x. And I'm going to talk about the approximate determinant method and the way that it leads to an improved error term in which the exponent is 7/12 plus epsilon rather than 2/3. And if you want to see the details, the paper is from Acta Arithmetica in 2012. Now, to get things started, we use the indicator function for n squared plus 1 to be square free, which you could represent as the square of the Möbius function of n squared plus 1. And one can represent this by summing over divisors d, for which d squared divides n squared plus 1 with a summand mu of d. This will pick out the values of n squared plus 1 that are square free. And we can rearrange this by putting the d summation first. So d here will run up to x, and we will have mu d, and then the number of n's for which d squared divides n squared plus 1. And then one can show rather easily that the terms up to square root x contribute the leading term that we had before and a small error. So what we need to do is to understand the contribution to this sum here from the values of d bigger than root x. And for these, we will ignore the Möbius function and just look at the number of solutions of d squared times a cofactor e equal to n squared plus 1, where n is at most x. So if you can give an upper bound for this quantity that is of order x to the 7/12, as in my theorem, then that will be sufficient.
Do you also keep using the fact that d is greater than the square root of x?
Yes, that will be important. The size of d is crucial. But for example, in fact, you're only interested in square free values of d because mu d will be 0 otherwise, but we're ignoring that contribution. Okay, so we'll split the available ranges for d and e into dyadic pieces. So we'll suppose that d runs from capital D to twice capital D, and e runs from e to twice capital E. And we'll count solutions d squared e equal n squared plus 1, and we'll assume that the parameters capital D and capital E satisfy this inequality, which corresponds to the fact that n is at most x. So what we need to do is provide an upper bound for this quantity here. So this is a question about an upper bound for the number of solutions of a Diaphantine equation. That's exactly the sort of thing that we talked about in the first lecture. Now, given the structure of this equation, it makes sense to analyze it over Qi. And you can see that d and e will have to be sums of two squares, and that x plus I, sorry, that should be an x2 there. X1 plus ix2 squared, y1 plus iy2, that will correspond to n plus I. And so the real part of this will be the number n, and the imaginary part will be 1. Now, the first equation says that something is equal to n and is less than or equal to the original value of x. That doesn't give us any information. And it's the second one which is of interest. So we have this equation here. That's the one that we want to study. Here it is again. And so what we're doing, if you like, is to count integer points. There are 4 variables, so this is an affine threefold. Well, I haven't, although I've mentioned affine varieties before, most of the results I've explained to you have been about projective varieties and have been about curves and surfaces in particular. So this sounds a little bit complicated. However, one thing one can do, and an important point of view for the approximate determinant method, is to think of this, ignore the fact that this is equal to 1, and just say that this is small. So we're looking at points near the surface where this quantity is equal to 0. And of course, this is a projective surface now. It's homogeneous of degree 3. Alternatively, indeed, because it's homogeneous of degree 2 in the x's and homogeneous of degree 1 in the y's, you can think of this as giving a biprojective curve in P1 cross P1. So there are 3 different points of view to handle our problem. And, well, which of these 3 points of view will be the most effective to use? Well, let's have a look at the estimates that come from the determinant method and consider the projective versions versus affine ones. So let's think of an absolutely irreducible polynomial in 3 variables, for example, of degree d. Now, I didn't actually state the results that the determinant method gives for affine surfaces, but f equals 0, because this is an irreducible polynomial in 3 variables, that will be an affine surface. The determinant method will tell you the number of points of height at most b, well, they will lie on b to the 2 over root d curves. However, if this happens to be homogeneous, f equals 0 will have at most order b to the 2 over d rational points. So if you think of this, if f happens to be homogeneous, you could regard f equals 0 as an affine surface and get something with an exponent 2 over root d, or you could regard it as a projective curve and get something with exponent 2 over d. So just comparing these 2 results, you can see that we get better results viewing the thing as a projective curve than we would as an affine surface. And indeed, going back to the previous slide, regarding this as an affine threefold would give a very weak result. Regarding this, well, if you could count points on the projective surface, that would give a much better result. And indeed, probably using something biprojective would give something even better. However, we've got to contend with the fact that we're counting points near the variety rather than on the variety. So the strategy is going to be to think of this as counting points near a biprojective curve. So let's see how we do that. Here's the equation we want again. For simplicity, I'm going to suppose that both x1 and x2 are of exact order square root d, and similarly that y1 and y2 are both of exact order e to the half. That will just keep things slightly simpler. I'm going to divide this through by y2 and by x2 squared, is that right? Or x2? No, by y2 and by x1, x2, and rearrange things, and what I get is an equation like that. I'll call the quantity on the right t, and I'll write s for x2 over x1, and I'll write phi for the rational function capital X minus x inverse, so that this equation here says that t is phi of s, plus this little bit here. That term there is quite small because x1 and x2 are of size d to the 1/2, y2 is of size e to the 1/2, so that's order d inverse e to the -1/2. And with the typical values of d and e we're interested in, that's of order x inverse. So if I think of the height of s as being the maximum of the numerator and denominator of s, that's of size d to the 1/2. Similarly, if I think of the height of t as the maximum of the numerator and denominator, that's of size e to the 1/2. So what I'm doing now is counting points st near the curve phi s equals t, with bounds on the height of s and t. and near meaning within order x inverse. So instead of having to worry about a threefold, I'm now concerned with a curve. And that's not only simpler, but it's going to, as I explained, to give a stronger result. Okay, so S was x2 over x1, and because of my choice for the range of x1 and x2, that means that S is of order 1. And what we're going to do is to split the S range up into short intervals of length capital U, where capital U is less than or equal to 1. So from S star to S star plus U. Now, splitting up the S range into short intervals is the Archimedean equivalent of splitting up the points in the p-adic method into congruence classes modulo p. So we localize the points that we're interested in into a short interval in one case, or a p-adic disk in the other. And we're just going to look at those points for which the corresponding S value lies in this short interval. So let's suppose we have points with indices from 1 through to capital N, and they all satisfy this equation here, as we've supposed. And then, just as before, we're going to form a matrix of monomials. They're going to be monomials in S and T. And we're going to put constraints on the exponents. There'll be monomials S to the I, T to the J, with I up to capital I and J up to capital J. So we have to think about how we will choose monomials, and it turns out that a good choice is to choose monomials with exponents in such a range. And capital K will then be the number of monomials. Now, I'm going to stress that we use all of these. We don't have a constraint corresponding to the one that said that the exponent En had to be less than some little d. We just use all the available monomials, and we'll see how that pans out in a moment. And then we form the n by k matrix with rows given corresponding to the different indices here, and columns corresponding to the different monomials here. So this matrix M0 will have its nth row consisting of monomials Si to the n, Tn to the j. And as before, we claim that the rank of M0 is going to be strictly less than, I should say K there, sorry, strictly less than K if the interval length here is chosen small enough. So that corresponds to the claim that the rank of the matrix in the p-adic version is strictly smaller than the number of columns if the prime is large enough. And then that will produce a null vector C, MC is equal to 0, and that will produce a polynomial F with f of Sn Tn equal to 0 for each value of n, for all the points that we're interested in. So just in the same way as we did in the p-adic version. And we'll get one such f for each of the intervals. And so we'll have polynomials f1 through to fr with r of order u inverse. That's the number of intervals we'll need. Good. Now let's remember that S was x2 over x1 and t was 2y1 over y2. So the values of Sn and Tn are rational numbers rather than integers. And so we can clear denominators by multiplying through by x1 to the I and y2 to the j, and that will produce a bihomogeneous polynomial fr of x1, x2 and y1, y2. And it will have by degree I, j. And so the outcome of all this is that all the solutions of the equation we're interested in have fr equals 0 for one of these r's here. Now, this equation here is inhomogeneous. There's a 1 at the end here. Whereas the FRs are, in fact, bihomogeneous. And so it's automatic that the variety given by this equation has no component in common with this homogeneous variety. So there's no necessity to artificially ensure that this FR is co-prime to some previous capital F. That's automatic because of the 1 here and the fact that this FR is going to turn out to be homogeneous. So that's how we were able to use all the monomials of degree up to ij rather than just a selection of them. Okay, so how do we prove that the rank of M0 is strictly less than, I should say K again, for U small enough? Well, we look at a square submatrix, and without loss of generality, we can make it the first K rows. Since S is in the interval from S star to S star plus U, we'll represent it as S star plus little u. Previously, in the previous lecture, at some stage in the argument, I said that we'll forget that things were ordinary integers and just suppose they're p-adic integers. Well, analogously here, we'll just remember that u is a real number rather than that it's some rational number minus S star. And then previously we used the implicit function theorem. Here it's going to be rather simpler. We'll just use an approximation involving a power series with an error term here. So we'll have phi of S star and u phi dashed of S star, and then an order u squared. Together with the order x inverse that we had before. So this is, you can think of these terms as the first 3 terms of the power series for phi s, given that S is S star plus u. It turns out that the optimal choice for capital U is between x inverse and x to the minus a half, so that this error term here is dominated by this one. So if we make that assumption about U, we can see that T is this linear polynomial in U plus a little piece V, which is of order x inverse. And so we'll use this to define V. So we'll now change from notation involving S's and T's to notation involving U's and V's. And that means that the terms in our matrix, which had originally been S to the I times T to the J, are now this shape, S star plus U to the I, and this linear function to the power J. So the entries in the matrix are just these simple polynomials in U and V. And then to show that the determinants are small, we use the same sort of column operations that we did in the previous lecture. I won't go through all that again, but we produce columns with successively smaller leading terms. There's a lemma that tells us how large the determinant M1 is going to be in that case. if you have bounds on u and v, well, u will be at most capital U, v will be at most capital V, which is of order x inverse. If we arrange those terms in decreasing order as t1, I should say t0 greater than t1, etc., then we have an estimate involving the product of the first, I should say k again, th's. And there's a proof in a previous paper of mine. But the point is that we get a nice small estimate for the size of det M1 because u and v are small. And you do a long and tedious calculation and you find that det M1 is exponentially small with a negative exponent capital T given by this expression and some rubbish here. And we're going to compare this Archimedean estimate for det M1 with the fact that since M1 has entries of this type with rational numbers with the denominator x1 and y2, if we clear those denominators, we're going to get an integer. So we'll conclude that the determinant is 0, provided that the product of this by this exponentially small thing is less than 1. So this is the condition that tells us that det M1 must be 0. When you work out what that means, and you make a sensible choice for I and j, so the terms s to the little I had exponent most capital I, terms t to the little j had exponent most capital J. We hadn't yet chosen I and j, so this is how you choose them. You find that the appropriate requirement for the interval length u is that log of u inverse should be at least this large. The outcome then is that for each of these short intervals, there's a corresponding bihomogeneous form such that each solution of the original equation satisfies f equals 0. And the degree of capital F is bounded in terms of this quantity delta here, small delta, and the coefficients of f are at most of order x to the kappa, for some kappa that depends on delta. We have some control over the size of the coefficients. So we've got this extra condition now, providing we're in this short interval. How do you use that? Well, one method is to forget about the original equation and just to use the bihomogeneous one. That seems slightly surprising, but you'll recall that I explained at the outset that we get much better estimates for homogeneous equations than for inhomogeneous ones, and we get results that are better still for bihomogeneous ones. So here's a lemma that says that if you have an absolutely irreducible bihomogeneous integer form with bi degree a comma b, then the number of solutions is x to the 2 over b plus epsilon times the size of g to the epsilon. So these are solutions in which x1 and x2 are co-prime, y1 and y2 are co-prime, and the xi's are of size at most capital X. So the exponent decreases with b, that's the degree in the y's, and you'll notice that there's no size constraint on y1 and y2. So this is really a remarkably sharp estimate for the number of solutions of a bihomogeneous equation. This result is essentially due to Broberg from 2003, but the precise version needed for this application is in the paper on square free values of x squared plus 1. So if the degree b here is at least 2, that gives an exponent at most 1 here. If b is equal to 1, you can use a rather different method. The bihomogeneous equation takes this shape. So you can see that y1 and y2 have to be given by d inverse g2 and minus d inverse g1, where d, because it has to divide g2 and g1, will divide the resolvent of the two polynomials. So there aren't many choices for d. And when you substitute these values of y1 and y2 into the original equation here, you get a further equation for x1 and x2. So it's only in the case b equals 1 that you have to use the original equation. Finally, one thing that you can do is to use the fact that your solutions lie in this short interval. And in effect, using this information reduces the effective size of x. I won't explain exactly how that comes about, but you get a saving of order u to the 1/2. You can swap the roles of x1, x2, and y1, y2 because the thing is bihomogeneous in both variables. And so the number of solutions is effectively this. And that then leads to the theorem I quoted. And it turns out that the worst case is when d and d are of the same size, x to the 2/3. Well, I've skipped some of the details, but I hope I've given you an impression of the general line of attack. So I'm going to end with a summary, well, of the determinant method in general. So in its local variance, you consider points in a small, either real or p-adic neighborhood. You construct a matrix with suitably chosen monomials, and what suitably chosen means may depend on the application that you're looking at. You estimate the determinants over R or QP as appropriate and show that they must vanish if your neighborhood is chosen suitably small. And you deduce then that the points lie on some sort of auxiliary variety, and you use that information. So there you have it, 3 hours of lectures summed up in 6 lines. Okay, thank you very much.